quick review for previous class. In previous class, we talked about the driving force for mass transport. So in order to quantitatively describe the magnitude of atomic flux, we use the atomic flux J sub I or sub 1, right? And based on the fixed first law, atomic flux can be expressed like as minus diffusivity concentration gradient, or can be expressed like concentration mobility times driving force. Here will be the minus chemical potential gradient. And in order to, in the first section, we introduce what's the diffusivity, these intrinsic material properties. What's the relationship between the diffusivity and mobility? Then we introduce there are three different kinds of diffusivity you are going to deal with in mass transport in solid materials based on different material system. Either is a homogeneous material or inhomogeneous material, and different reference coordinate. And so let's move to the first part is we based on the atomic flux can be expressed like mobility, concentration driving force, and minus diffusivity concentration. And after series deviation, we can get that the mobility of the moving diffusing atoms is proportional to the diffusivity of these moving atoms in these materials. So the relationship is proportional. So now you can use the diffusivity to describe how fast the diffusing atoms diffuse through your materials. And next, we introduce three different types or kinds of diffusivity. And the first one is a self-diffusivity. Start D only happen, or we describe this diffusivity in chemically homogeneous medium. That means within these materials, the concentration is uniform, and there's no concentration variation along your materials. Either can be the pure materials or the alloy, as long as the concentration is uniform along your materials. Then the diffusivity we measure is a self-diffusivity, star D. And when you deal with, if your system is inhomogeneous materials, that means there's a concentration variation along your sample. For example, like the diffusion couple, then we can use either intrinsic diffusivity, D, or interdiffusivity to describe how fast the diffusing atom moves in your materials. And the difference between these diffusivities is the observation coordinate. Intrinsic diffusivity, we describe this diffusivity in crystal coordinate. That means you stand at the interface or inside the material at a specific plane. Then the diffusivity you measure, we call it as an intrinsic diffusivity. And however, if you stand outside the material in the lab, then we call, and the diffusivity you measure or observe, we call it as interdiffusivity. And the following slide, and this is some schematic showing that interdiffusivity, the intrinsic diffusivity means you stand in the materials, and interdiffusivity means you stand outside the materials. So there's a reference coordinate is different. Okay, so following slide is going to demonstrate and develop, deviated what's the relationship between the diffusivity and direct or coupling coefficient. And as you know, the self-diffusivity as long as you want to measure that, you need to put the radioisotone to label some of the atom. Then you measure the diffusion profile of this labeled component. Then you will get the star D, right? And can be expressed like this, and is related to the direct and coupling coefficient, and also the concentration of the component I. And for the intrinsic diffusivity, as we mentioned, it only happens in the chemically inhomogeneous material system. So as long as the diffusion happens, the interdiffusion happens, then the diffusivity you measured is related with what? Is the gamma, is the activity coefficient, and also the self-diffusivity of this diffusing atom A. And the gamma actually is related to the ideal or non-ideal the mixture of ideal or non-ideal solution, right? The gamma. So if the mixture between 1 and 2 or A and B is obey the ideal solution, the gamma will be equals to 1. Then at that case, you can drop this term out. So the intrinsic diffusivity will be equals to self-diffusivity of atom R1. So we remark that here is if it is an ideal solution or dilute solution, then the self-diffusivity will be equals to intrinsic diffusivity. Okay, and the other diffusivity we call it the interdiffuivity. That means you stand where outside your materials, so you need to do some correction or modify on the flux. We call it the J1 prime and J2 prime. And because you stand outside your material system, so as long as the interdiffusion happens, the interface is going to move. We assume it goes to this right-hand side, these directions, and with the velocity v. So the J1 prime, you need to plus you got the extra amount of atom passing through this interface. So after series deviation, then we can get the diffusivity. Interdiffuivity here will be related to the diffusivity of atom 1 and 2, and also the atomic fraction or composition of this diffusion couple. And just remind you, we only have one interdiffuivity, because when you have a look on the J2 prime, this D interdiffuivity is the same with this one, so we only have one interdiffuivity. And if you make some, in order to simplify the interdiffuivity, if the X1 is very small, that means the dilute solution, then this very small, so X2 will be equals to 1, and you can directly drop this term out. Then you got the intrinsic diffusivity will be equals to interdiffuivity. So if we make a summary, as long as the diffusion happens, the diffusion regime happens in ideal solution or dilute solution, the self-diffusivity will be equals to intrinsic diffusivity, and also will be equals to interdiffuivity. So that's why in previous class or previous course, that when the book mentioned the diffusivity, it don't only give you a specific of certain value of diffusivity assigned for specific atoms diffused in materials. And actually, they make a very important assumption. That means it definitely this AB diffusion couple or this diffusion of AB or 1 and 2, this kind of diffusion, interdiffusion, belongs to either ideal solution or dilute solution. So you can consider all all diffusivity equals to 1. The value for list 3 diffusivity are the same. So assign for a specific value for this. Then we were going to move to the application for interdiffusion. There's a very famous interdiffusion. The example for interdiffusion, we call it the Kirkendall effect. What's the Kirkendall effect? It happens in the diffusion couple. We have material A and bind with material B and to form a diffusion couple AB. And here you can first of all this diffusion couple is in homogeneous medium or in homogeneous materials, right? Because the concentration of atom A is different along these materials and also the material B, right? So the mass transport of two components A and B with this similar diffusion rate in this alloy or reaction system, that tell you the JA won't equal to JB. Now in this case, the JA is larger than JB, and based on the network constraint, or the summation of total flux will be equals to 0. So you got because JA is larger, right? So there's a vacancy flux to compensate the JA, right? So we got the JV plus, or JV vacancy of flux plus the vacancy of B atoms equals to JA. And also, in this kind of situation, Kirkendall effect tell you that you can observe two phenomena. The first one, we call it is Kirkendall void formation. Because there's a vacancy flux toward to left-handed side, so you will observe the void form at material A side in the material A. And also, if you put the marker at the interface, you also can observe the Kirkendall plane shift. That means this plane is going to shift. In this case, because JA is larger than JB, that means at the unit time period, in the unit time period, the more A move to right-handed side, right? So the plane is going to be shifted toward to left-handed side. So if you put a marker at the interface, then you can observe the plane, the interface, or this marker. This plane is going to shift toward to left-handed side. So this is so in this case, if you, for example, like some people will do the diffusion couple like the zinc and the copper, and you heat this diffusion couple up to high temperature, and that will allow the interdiffusion happens. And after a certain time period, you can observe what the void form at the zinc side, and also the marker, the interface, is moved to the zinc side as well. And because there's an diffusion happens between zinc and copper, and they also sometimes they will form some chemical, they will react each other to form, in this case, there's a new chemical compound we call a brass form in between zinc and copper. So we can see the AB, there's a new material brass form in between zinc and copper. So this is this is a Kirkendall effect. You can observe the void formation and also the plane shift. And that's the other cases. Also is a Kirkendall effect. We call it a metal oxidation. If you want to oxidize the copper substrate, usually what you will put the copper substrate into the oven probably and heat it up, right? And and flow the oxygen gas to form the metal, the copper, to form the oxide, right, on the copper. So if you draw the flux, the simple schematic for this flux, the metal flux here, the metal flux J metal is larger than the flux of oxygen. So it also, you can observe the dissimilar flux, right, between two materials. And so in order to get the net flux equals to 0, so that will lead the vacancy flux downward, right, toward the bottom. So this is also the Kirkendall effect, right? For the criteria of the Kirkendall effect, the first one is that you have two different compounds, and there's a concentration variation along these materials. Yes, there's similar flux, yes, and we got the vacancy flux here. So based on this concept, you can observe the vacancy at the metal side. Here is the copper side, because the J copper is larger than J, the flux of oxygen. Based on this, you can observe some vacancy presented at the copper side, right? And also, this is Kirkendall effect. So as long as there's a vacancy flux, so you also should observe the void and also the plane shift, right? So what kind of situation? What kind of situation will allow you to see the lattice plane shift? If the vacancy flux, if the vacancy flux is very small, and this vacancies were observed by some defect sink, for example, like a dislocation that give you like this excess row of the atom, right? And if we let the vacancy flux is very small, this vacancy probably will replace this atom. As long as the vacancy replaces all the atoms shown in this dislocation, and this dislocation is going to disappear, right? So that will allow this plane interface or lattice plane shift toward to the metal side. So this is at this situation, then you will observe the plane shift. And sometimes, if the vacancy flux is quite large, and that means the numbers of vacancy is larger than the dislocation site, then at this situation, the vacancy probably will accumulate and grow to form the void at the metal side. So sometimes, in most of cases, you will observe these two effects. But some people will ask me, in what kind of situation we will see more lattice plane shift than the void formation. So if there's in your materials there are enough dislocation, enough crystal imperfection site to allow be replaced by the vacancy, then probably you will observe more lattice plane shift. Or if the void formation energy is quite high, then also the vacancy is will replace the dislocation instead of to grow to form a void. or the growth rate of a void is smaller or slower than the diffusion rate of vacancy through these metal materials, then that will allow the vacancy will prefer to move and replace the, uh, the atoms instead of accumulate and form the void. So if you want to observe, if you observe more void form in your material system, that implies that the void formation energy is lower, and also the growth rate is higher or faster than the diffusion rate of the vacancy diffused through these materials. Okay. So next, I'm going to show you some experimental results. Some people or some scientists observe the Kirkendall effect. So let's take a look on this simple schematic. In this case, we have a zinc copper diffusion couple, and as you know, the flux of zinc is larger than the flux of the copper. So this will result in a vacancy flux downward. And based on this flux, vacancy flux, the direction of the vacancy flux, you can expect it at the zinc side. You can observe there's a vacancy, and probably vacancy will nucleate to form a void, right? And as we mentioned, the diffusion also happens at the interface. So this will form some new compound. This is the zinc copper alloy. We call it the brass. You can observe the brass during the diffusion. The brass gets thicker and thicker. This is the chemical reaction. So this is the experimental observation. And with increasing time period, what we have here is in the beginning of diffusion, the author put the marker at the interface of the zinc and copper. And with diffusion, after a certain time period of time, you can observe what the thickness of the brass gets thicker and thicker during the diffusion over time. Okay, and this is the case for zinc and copper. And also, we also can observe the Kirkendall effect on the other diffusion couple is copper and tin. As we know, the copper flux is larger than tin, the flux of tin. So that will result what the vacancy flux will toward to the upper side, the copper side. And so you can observe some void formation at the copper side. And also in between the interface, there's an interdiffusion. The interdiffusion happens at the interface, right? So we can observe the copper tin alloy form at the interface. We call a chemical reaction. Okay. So this is the Kirkendall effect. And some scientists also use the Kirkendall effect to prepare some narrow particle or narrow wire of materials. So if you have, you can prepare the core shell structure. The core will be the material A, and the shell you can use the AB alloy as a shell. And after Kirkendall effect, you can prepare this four A, B, C, D, these four different geometry of your narrow particle through the Kirkendall effect and also the surface diffusion mechanism. For example, like if you in the beginning you use the A material as a core and AB as a shell, right? And because the flux JA is larger than JB, JA is larger than JAB, so that will lead the vacancy flux toward to the center And so you can observe either the large hole inside your structure, or you can regard the small void formed at the A side. And if you allow this diffusion happens for a long period of time, in order to minimize the total surface energy of the system, this small void will merge to form the large void, like this way or this way. Then, if at this moment, let's present some channels on the core, on the shell, like this, then this tunnel will allow some material A to evaporate it or goes out. Then you can fabricate this kind of nanoparticle with this spatial geometry. And this channel or tunnel can also allow you to load some drugs or add some spatial compound into this narrow particle and serving as a drug carrier or some material carrier for different applications. And this is the nanoparticle, the case for manipulate different hollow nanoparticles by Kirkendall effect. And some sometimes it also use this Kirkendall effect to prepare the hollow narrow wire. And the story is like this. In the beginning, the authors prepared the zinc oxide narrow wire, and the diameter just 10 to 30 nanometer, and the length is 2 centimeter. It's a very long narrow wire, and he deposits a very tiny or thin layer of alumina on the top of this zinc oxide, spreads like a yellow one. And as we know, the zinc oxide, the flux of zinc oxide is higher than the flux of alumina. So that also will result a vacancy flux toward to the center of this nail wire. So that will allow what? Then you will the author successfully prepare the zinc alumina narrow tube, and this is a hollow tube, and this hollow is due to the vacancy flux. Probably in the beginning is the void, and based on the surface diffusion to lower the surface energy of the system, this is tiny void will merge together to form this hollow structure. So this is also the application of the Kirkendall effect in material synthesis. So I will give you a summary of diffusion and the Kirkendall effect. In this first section, the diffusivity, which we use this to describe how fast the atoms moves through your materials. And this diffusivity is defined by this first law, and also based on different chemical homogeneity and also the different observation coordinate, then you can get the self-diffusivity, intrinsic diffusivity, and interdiffusivity. And if we assume it's an ideal solution, dilute solution, then this diffusivity are the same. I mean, the value for this diffusivity are the same. If not, then there will be a different. The value will be different. And we also introduce you a very important concept is the summation of the total flux must be equals to 0, or you can call it the net flux at specific plane in your materials should be equals to 0. And at the end of these sections, we introduce a very famous effect we call the Kirkendall effect to well describe the interdiffusion phenomenon. And there are two characteristics be observed in Kirkendall effect. The first one is the interface is going to move toward to the side with faster moving species. And also the void will form at the wave. The void will form at the, uh, the material with faster moving species, right? Okay, so that's we already ended the first section.